everyone, welcome back to Easy Taleem. This is lecture 15 of our complete AS Mathematics course for 9709/12. Um, Last lecture we completed arithmetic progression on Saturday last week. Today we finished the entire series chapter, which by the end of today's lesson you will understand the geometric progressions, the nth terms, the sum of geometric progressions, and the sum to infinity, and when infinite series converges, when the common ratio is between 1 and -1. And finally, the difficult past paper style questions students usually leave until the end. So grab your notebook. This lecture is extremely important because GP appears not only inside the series chapter, but Cambridge quietly inserts them and combines it with logarithms, functions, trigonometry, and even modeling. So let's begin. Last lecture, we kept adding. So we talked about a constant difference, which was D, which we defined as the difference between the two subsequent terms, right? Or term n minus term n minus 1. Okay. Now, so an arithmetic progression looks like 3, 7, 11, 15, and so on, with a common difference of 4, let's say, right? Now, so this was constant addition. Now, geometric progression looks something like this. So maybe 3, 6, 12, 24, 48. Now, can you tell what is happening? Is this a constant difference? No, but it is a ratio actually. So 6 upon 3 is same as 12 upon 6. So this upon this, this upon this, this upon this, the ratios are constant between the subsequent terms, right? So we say that this is the common ratio, which is +2 here, right? So this is the entire difference. One chapter grows linearly. So arithmetic progression, it grew linearly like a straight line graph. Like I told you as well, that it behaves like a discrete y equals to mx plus c. Okay. Now the other chapter, the geometric progression, it grows exponentially. So if the first term is 3, the second term is a multiple of 2, right? So that becomes 6. The third term is going to become 12. So the graph is going to go exponentially high. Okay, and that difference explains half the modern world. Now you can model the population by this, compound interest, viruses, inflation, algorithms, everything, right? Now what really is a geometric progression? If I write down 2, 6, 18, 54, 162, etc. Now, what is changing? So there is a +4, there is a +12, there is a +36, and so on. But this is not constant, like, right? So the difference is not constant. However, if I look at the multiple, so 2 times 3 is 6, 6 times 3 is 18, 18 times 3 is 54, 54 times 3 is 162. So the ratio is common for this, right? Now, each term gets multiplied by a 3 exactly. Now, this multiplying number is called the common ratio. I'd rather that you guys keep taking notes here. Now, so we say that the first term of a geometric progression is also called A. We will use the notation A for the first term, and we will denote the common ratio by small r. Okay, so this is the common ratio. Now, exactly like arithmetic progression, which had A as the first term and D as the common difference, it had a difference. Geometric progression has a ratio. Now, so if I write the same down, 2, 6, 18, 54, 162. So 2, 6, 18, 54, 162. So can I write it as 2 times 3, 2 times 9, which is 3 times 3, 2 times 27, which is 3 times 3 times 3. Sorry, my bad. Wait. 3 times 3 times 3, and 162 may be written as 2 times 81, which is 2 times 3 times 3 times 3 times 3. Now, this is term 1, this is term 2, this is term 3, term 4, term 5, and I can also rewrite it as this one as 2 times 3 power 1, this is 2 times 3 power 2, 2 times 3 power 3, and 2 times 3 power 4, and this I can rewrite it as 2 times 1, which is 3 power 0, right? in terms of the common ratio. So this is the first term, this is the common ratio. So the nth term would be, as you can see, it would, so the 2 is constant, the 3 is constant, but you can see that the power is 1 less than the term number, right? So this is n minus 1. So I can rewrite any term in a geometric progression as the first term multiplies by the common ratio raised to the power of n minus 1. Okay, so I hope that you noticed this, the behavior of the exponent. The exponent is always 1 less than the term number. So yeah, so I don't want you guys to memorize. We derived it, right? So the pattern continues like this in a geometric progression. Therefore the nth term is going to be term n is equal to a multiplied by r, the common ratio, where a is the first term and r gets multiplied to it with the power of, with the exponent of n minus 1. Now if I give you a word example, let's say that I want you to find term 8 for a progression which is 5, 10, 20, 40. So I can quickly spot that my first term is 5. My common ratio is going to be what? It is going to be the ratio of the two terms. So 10 upon 5, 20 upon 10, 40 upon 20. So that's constant as 2, right? So the common ratio is 2. So term 8 is going to be a multiplied by r, which is 2 to the power of 8 minus 1, which is 7. Okay, so that's it. So this is how you have to do 5 multiplied by 100 and 5 multiplied by 128. Okay, now what if I give you another example and I want you guys to pause the video and solve it. The fifth term is 1 and r is 1/2. I want you guys to find term 8. So pause the video, solve it. I hope you guys have solved it. Now let me do it for you guys. So term 5 is 1. So I can rewrite term 5 as a r n minus 1, 5, which is 5 minus 1, which is 4. So n r is already given as 1/2. So a multiplied by 1/2 to the power of 4 is equal to 1. So I can find out a from here, because this is a multiplied by 1 upon 16. So a is nothing but 16. So I have a, I have r, which is half, and I can find term 8 very easily. So term 8 is nothing but a multiplied by r to the power of 7, 8 minus 1, right? So 16 divided by 128, whatever that is, so 4, 32, so 1/8, right? So that's going to be my term 8 is going to be 1/8. Okay, so that's as simple as that. Now, so many students immediately try finding the first term. Sometimes you don't even need to do that. Sometimes dividing equations is faster. We'll use that trick now. Now, let's say I give you second term is equal to 12 and fifth term is equal to 40.5, or I can write down 81 upon 2, right? Now, you are supposed to find out first term, common ratio, nth term. So find out a, which is term 1, which is a. We don't know what that is. Find out the common ratio, we don't know that, and find out a general term, right, in terms of r and the first term. So I can rewrite the second term, which is a times r, n minus 1, 2 minus 1 is just 1, so that's 12. And this one is a multiplied by r to the power 4 is 81 upon 2. So I can compare the a's, which is going to be 12 upon r is equal to 81 upon 2 times r4. So 1 r cancels 1 r here. So I'm left with 3 r's here and 2 goes there. Basically bring the 2 down here. So 81 upon 24 is equal to r cube. So this becomes, if I factor it by 3, so that's 27 upon 8. 27 upon 8 is, and take the cube root of that in order to find r. So that's nothing but 3 upon 2. So r is going to be 3 upon 2. So if r is 3 upon 2, plug that in here. So that's going to become 8. A is going to become 8. R is going to be 3 upon 2. And term n is going to be, a is 8, r is 3 upon 2 multiplied by n minus 1. Right? So that's going to be the general term as well. Okay, so that's it. The application is lagging, so I'm just resetting it. Okay, so Did you notice that there were no simultaneous? So of course simultaneous equations were involved when we tried to solve it, or we could have divided both the equations directly. But also that's also a trick of under which comes under simultaneous equations only. So there was no mess, and Cambridge definitely loves this shortcut. Now there are a few common mistakes that students make every time that we go through the examiner reports. So the first one is that students write term n as a multiplied by r to the power of n. That's horrible. Never do that. Never ever do that. So this is absolutely wrong. Term n is a multiplied by r to the power of n minus 1. Exponent is n minus 1 always. The second mistake is that they take difference instead of ratios. So geometric progression will never ask you for the difference. Okay, it always asks you the multiples. Okay, the multiple could be greater than 1 or less than 1. It can never be 0, it can never be 1, because if the common ratio is just 1, then all the subsequent numbers are going to be identical, right? Now there are negative ratios as well. So for example, if you have a series like, so that's a third mistake, 4 minus 8 16 minus 32. So the common ratio is what? Minus 8 upon 4 is equal to 16 upon negative 8 is equal to negative 32 upon 16. So that's negative 2. So r is going to be negative 2. The common ratio, just like common difference, can definitely be negative. Okay, so sign and the sign definitely matters both here in arithmetic progression as well as in geometric progression. And Cambridge loves hiding these traps in your APGP questions, because the students make these blunders. Now, what is the sum of a geometric progression? Now, finding the 100th term is useful. So you can find out the 100th term if you do have the a and the r. But what if I ask you that if the first term is 2, the second term is, let's say, 4, and then 8, and then 16, and then 32, where the common ratio is 2, where the first term is 2. What if I ask you to now add 100 such terms? So you go all the way till the 100th term and start adding them, right? Now this becomes tricky, right? So you can keep on adding, that's possible, but what if there are 100 terms, 1,000 terms, 10,000 terms, 500 terms? That's not possible, or it becomes very tedious. So just like in the last lecture, today we are going to prove the sum of the geometric progression. Okay, the sum of the geometric progression, and we are going to derive it ourselves. Not so you don't have to memorize it. Since we will derive it, that proof will be the foundation of every GP question that you are going to face in Cambridge. So the sum of a geometric progression is a multiplied by 1 minus common ratio to the power of n divided by 1 minus common ratio, right? Now, if you look here, what I can see is that if I multiply both the sides by 1 minus r, I get Sn minus r times Sn, right? Which becomes a multiplied by 1 minus Rn. Now this gives me that, okay, if I'm adding these, if I'm taking a difference of these two, so what is a general sum of n look like? So the first term is a, the second term is ar, the third term is ar square plus dot 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 plus ar n minus 1, right? So for n terms, the last term is going to be ar n minus 1, right? Now if I multiply this entire thing by r, so this becomes ar, this becomes, the second term is going to be ar square, the third term is going to be ar cube, second last term is going to be ar n minus 1, and the last term is going to be ar n. Okay, now you saw something that we take away this thing, which is this thing, from Sn. So if I do this, so if I take a difference of these two equations, this is equation 1, this is equation 2, so this is going to become Sn minus r times Sn. So a minus nothing, so this becomes a, plus ar cancels ar, so all of these gets cancelled, and only this remains. So this is also going to become plus. So all of these gets cancelled. So I'm going to be left with a minus arn, right? Can you see? And I can take a common. So this becomes 1 minus r to the power of n. And I can take Sn common from here, and this becomes 1 minus r. So Sn formula now is a multiplied by 1 minus r to the power of n divided by 1 minus r. And that is it. It is as simple as that. So this is not a formula. This is this is not a formula you memorize. This is a formula you can rebuild in just 30 seconds, just like you saw me do it here, right? And whenever you want to prove something, just see what the composition of the end result looks like, and if you can go back a step, if you can go a step backwards. Okay, now sometimes Cambridge also rewrites it as you just multiply both the numerator and denominator by -1, and you will get, so that's another form of the very same formula, a multiplied by Rn minus 1 upon R minus 1, which is one and the same thing, right? So you don't have to panic. Just multiply numerator and denominator by a -1 and you obtain exactly the same thing. Therefore, both are identical. Use whichever you find easier. Now, there's a very practical tip. If your common ratio is between 1 and -1, okay? So I personally prefer this one, right? So this formula is more useful for when your R is greater than 1, right? But a lot of students find this one as well. No, sorry. This one is useful when your R is greater than 1, but you can use this one as well if you're. I mean, both. A lot of students have different preferences. I wanted to share with you how students usually do it and what examiner reports talk about it. However, I will leave it to you to find your comfort zone while doing the exercises from your notebook. So I want you guys to go to your Cambridge notebook. I hope you have already done the arithmetic series questions after the last lecture that you saw on Saturday last week. Today you should start doing the geometric series questions from your Cambridge Indoors Black Book. If you don't have the digital copy of that, you can WhatsApp me on +92 329 3028485. I will send it over to you. You can also follow us on our Instagram, where we go by the name of EASYEZ Taleem, TALEEM. Now, you can, just like I said, you can use either of the two formulas. It's one and the same thing. Now, let's do a worked example for sum of geometric progressions as well. Let's say that you have to find out the sum of this series, right? Now, what is happening here? No. And it's an infinite series, right? So for an infinite series like this, you cannot find the sum to infinity, right? Let's say if I ask you to find the sum of 12 terms, so you know the formula, a multiplied by 1 minus r to the power of n. In the sum formula, it's not n minus 1, it's just n upon 1 minus r. Now your first term is 3. Your common ratio is 6 upon 3 or 12 upon 6, which is just 2. So 1 minus 2 to the power of 12 upon 1 minus 2, right? 1 minus 2 is -1, so you just put a -3 here, and the negative inside the bracket is going to turn it into a positive eventually as the last result, and now you can find out the answer, whatever that is. So 2 power 10 is 1024. 1 minus 4096 times -3. So this is negative, this is negative. Eventual result is going to be positive, whatever that is. I don't want to get into the mess now. So that's very easy. Now, if you have, let's say, if you want to add 5 plus 2.5 plus 1.25 plus 0.625 plus ... and sum to infinity. Let's say I ask you to find the sum to infinity. Now, sum to infinity is going to become, now the first term is going to be 5, 1 minus r. R is going to be what? 2 upon 5 divided by 5, which is half. 1.25 divided by 2.5, which is half. So this, and there is infinity, and 1 minus ratio, right? So in the denominator, 1 minus half is just half, so I will just write down half. Now, and 5 divided by half is nothing but 10, so I will write down this. Now 10, and now 1 minus half. Now, if this is a number which is less than 0, when you multiply it a million times with itself, I mean, even if you raise half to the power of 50, you are going to get a very, very minute quantity, right? Let alone when you multiply half by itself an infinite times, right? So it's going to disappear, right? So this is going to become 0. So your answer is going to become 10. Now let's do a physical demonstration of this. So let's say you first travel 5 units, then you travel 2.5 units, so a total is 7.5. Then you travel 1.525 units, then 0.625 units, and then 0.3125, and then even smaller. So this is 7.5, 8.75, 9.4 something, then 9.7 something. So you will get closer and closer and closer to 10, but you will not reach 10. You will only reach 10 when you will have multiplied this 1,000, I mean an infinite number of times. So infinite will be a quantity which usually we cannot, which we can never express, right? But if should you be able to reach this 10, you will say that it was multiplied by itself an infinite number of times, right? So this is only possible, this becomes zero only and only, or we use a notation if and only if your r is less than 1, right, but greater than -1, and r cannot be equal to 0. So if your quantity is between 1 and -1 where r is also not equal to 0, then sum to infinite is possible, and we will say that it converges to 10 or a certain quantity, right? So it's only possible then, right? Now, there are common Cambridge mistakes here as well. So I can write a general formula as a upon 1 minus r. Why? Because 1 minus r to the power of n, when r is between 1 and -1, it just disappears. It becomes a 0. So a times 1 is just 1. So we don't write anything and we just leave sum to infinity ratio as this, where this has to be a convergent series, right? Now, so just like I said earlier, the common mistakes that Cambridge always identify and talk about in their examiner reports is that they use a multiplied by 1 minus r to the power of n minus 1 and just screws it all up. Please do not do that. There is no -1, and we derived this formula, right? So you have to be sure that there can't be a -1, and we also derived the formula for the term, and we saw that there's an n-1 there, right? So term n is a multiplied by r to the power of n-1, and sum of n terms is a multiplied by 1 minus r to the power of n upon 1 minus r, and sum to infinity is nothing but a upon 1 minus r, where r is between 1 and -1, and of course r can never be equal to 0, and for no geometric progression can r be equal to 1, because then all the subsequent terms are just going to be equal, right? Now mistake number 2 is that students use wrong ratio. They do divide. So if you have 2 plus 4 plus 8 plus 16, you can see that 4 upon 2 is 2, 8 upon 4 is 2, 16 upon 8 is 2. What students do is they divide 2 by 4, they divide 4 by 8, they divide 8 by 16, and it also just destroys all the marks that they get, or they could get. Now, you don't put brackets in your calculator. So you will put 2, you will put 1 minus r, which is 2 to the power of n. Let's say you're finding the term of 20 terms, and 1 minus r, which is 1 minus 2. You forget to put these brackets. And if you forget, so you will press 2 multiplied by 1 minus 2 to the power of 20, and you will press divided by 1 minus 2, divided by 1 minus 2. So what your calculator is going to do is it's going to multiply 2 by 1. It's going to divide 2 to the power 20 by 1, which is going to be nothing but 2 to the power 20. Then it's going to divide -2. So 2 cancels -2. So your answer that your calculator is going to produce is going to be -2 to the power of 20 multiplied by a -1, right? So don't do that. Don't do those mistakes that you shouldn't, right? Now, if you have something like 1.333333, for example, and it's a recurring decimal, okay, which you also write as 1.33 and these dots. Now, can I also rewrite it as 1 plus 0.333, and can I also rewrite it as 1 plus 0.3 plus 0.0333, and I can rewrite it as 1 plus 0.3 plus 0.03 plus 0.00333. So the 0.3 is what? 3 upon 10. 0.003 is what? 3 upon 100. And then I can rewrite it as 3 upon 1000, and then 3 upon 10,000, and so on, right? And there is a +1. Don't forget that. We have to prove that this 1.333 is same as 4 upon 3. Let's see how we can prove that. Now, let's keep it separate, because this is not part of that. Now, if I take this as the first term, so a is going to be 3 upon 10, And by the way, this goes on and on and on to infinity, right? There are infinite number of terms because this is a recurring series, right? So the common ratio is what? This upon this, and this upon this, and this upon this. So it's nothing but 1 upon 10. So R is going to be, and you can do it, you can divide the two subsequent terms. So R is going to be 1 upon 10, A is going to be 3 upon 10, and we can do sum to infinity. So sum to infinity is what? A upon 1 minus R. 1 minus R. R is 1 upon 10, right? So this becomes 3 upon 10 divided by 9 upon 10. 10 and 10 gets cancelled. So this becomes 1/3. And then you add 1/3 to this 1, which was here. So 1 plus 1/3 is nothing but you take the LCM 4 upon 3. And this is how you can get. So if I give you 1.98888, and I want you to find me the exact term, so you can separate 1.9 and then start writing 0.08 plus 0.008 plus 0.0008 plus so on and so forth. So 1.9 is, so 1.9 you can write as 19 upon 10 plus this is 8 upon 100, 8 upon 1000. Again, the ratio appears to be 1/10. So R is 1/10. For this geometric progression, A is 8 upon 100. So I can easily put it in the formula, which is A is 8 upon 100 upon 1 minus R. R is 1/10, which is just 9/10. So this becomes, this cancels this. So 8 upon 90 plus 19 upon 10. Now you multiply it. So this becomes 19 times 90 plus 8 upon 90. So this is going to give you the exact fraction for 1.9888 recurring decimal. 1.988. Okay. So this is how you do it. Now, so this is all concepts of conversions. The extra pieces become smaller and smaller and smaller, and eventually they become practically zero. And mathematically, this R to the power of n approaches zero as n becomes very large, and R is between 1 and minus 1. Right? This is very important. Now, we know the sum to infinity. We know the sum of n number of terms when R is greater than, or when R is any value, right? Now, so let's do a worked example. Let's say you have to add 4 plus 3.2 plus 2.56 and so on. I can see that my ratio is going to be 0.8. Okay, and I have to find sum to infinity. So it's nothing but A upon 1 minus R. Now it's very easy. 4 upon 0.2 is nothing but 20. Okay, so very easy. Now, so this is where we are going to do something where Cambridge separates A students from A star students, right? Now, if I give you, and this is something that I uploaded on in my stories as well today on Instagram. Let's say a ball is dropped from 8 meters. This is 8. The ball is here and it's dropped. Every bounce reaches, so it comes here, and then the next bounce is 3/4 of the previous quantity. So 3/4 of that is 6. And then 4.5, right? So you have to find the total distance traveled. So this is 8, this is 6, this is 6, this is 4.5, this is 4.5, this is whatever 3/4 of 4.5 is. I think that's going to be 3.375. 3.375 plus 3.375. So if I look at it, so this is 8 plus 6 times 2 plus 4.5 times 2 plus 3.375 times 2 plus ... right? Because eventually it gets smaller and smaller and smaller and smaller and lands here. So the twice happens, right? Now you can take a 2 common and you will get 6 plus 3/4 of 6 plus 3/4 square of 6 plus 3/4 cube of 6. So essentially a geometric progression, right? Now, so I will leave this as it is, I will leave this as it is, I will leave this as it is, and I will treat this. Now my first term is this 3 upon, no, I can take my first term as 6, okay, because this is 6 multiplied by 3 upon 4 to the power of 0, right? So A is 6, sum to infinity, 1 minus R. 1 minus R is 3 upon 4, which is 1 minus 3 upon 4 is nothing but 1 upon 4. 1 upon 6 divided by 1/4 is 24. So this square bracket sum is nothing but 24. 24 times 2 is 48. 48 added to 8 gives you 56. So a total of 56 meters is traveled by the ball. Okay, so this is as simple as that. Okay, so the first drop is not doubled because it just gets dropped, right, just one way, and then every subsequent journey is doubled because it goes up and comes down, goes up and comes down, but by a fraction of that, right, 3/4 or 75% of that. So this is a favorite Cambridge application. Now what if we say that there is a charity and it sees that the donation grows by 10% every year that they collect, right? Now, what if they want to find out the total donation after 7 years? So the donation after 7 years is going to be, let's say we don't know what the first year's donation is. So we just do 1 minus R, which is 1.1. So R is going to be 1.1. So in the first term, if it is 1, the second term is going to be 1.1a. The third term is going to be 1.21a. So right? So you probably know this from your O levels and GCSE anyway. So 1.1 to the power of 7 upon 1 minus 1.1. So whatever the principal amount is in the reference here, you just do this ratio and find the sum of donations in the 7 years where every subsequent donation is increasing by 10%, right? Now, what if you had to find K if the first three terms are K plus 12, K and K minus 9? And form a and these terms form a geometric progression, right? So of course the ratio must be same. So this upon this must be same as this upon this, right? So K minus n upon K should be equal to K upon K plus 12. Cross multiply, so you get K square plus 3K minus 108 is equal to K square. So K square gets cancelled. So 3K is equal to 108, or K is going to be equal to 36. That's it. It's as simple as that. Now, let's do further AP and GP questions. We are going to connect both lectures, the lecture from last week, Saturday, and the lecture that you have just gone through now. So sometimes Cambridge mixes both arithmetic progression and geometric progression. Let's say A, B, C are in arithmetic progression. A, B, and C. Now, what does that mean? That the difference is going to be equal. B minus A should be equal to C minus B, right? So 2B should be equal to A plus C, right? As simple as that. Now, if A, B, C are a geometric progression, so this is arithmetic progression. If A, B, C are a geometric progression, then we will say that C upon B is same as B upon A, or we will say that A times C is equal to B square, right? Now, so they appear regularly. Students usually forget them, and you can easily form one equation in terms of A and C by just taking the square root of AC here. So that's going to be A square root of AC is equal to B, and B is equal to A plus C upon 2, and then you can compare both the B's. So this is going to become A plus C upon 2 whole square is equal to AC. That's it. So this is another equation that you can form. Now, the last questions of this chapter combine arithmetic progression, geometric progression, functions, trigonometry, and algebra. So you don't immediately hunt for formulas. Ask yourself, what type of progression is this? Now, so let's review everything. We did arithmetic progression. We did common difference. We saw that in arithmetic progression, the term is A plus n minus 1 times common difference, where A is the first term. The sum of n terms is nothing but n upon 2 times 2a plus n minus 1 times d, or if you know the last term, it's going to be n upon 2 times a plus l. That's it, right? So you know this. In geometric progression, let's use green color. Term n is going to be a multiplied by r to the power of n minus 1. Sum of n terms is nothing but a multiplied by 1 minus r to the power of n whole thing divided by 1 minus r, and sum to infinity, if your common ratio is between 1 and minus 1, is nothing but a upon 1 minus r, because this r to the power of n, when n approaches infinity, r to the power of n approaches 0, right? So this is only, sum to infinity is only an extension of sum to n terms formula, right? Provided that your common ratio is between 1 and minus 1. So it's going to converge. Now, So congratulations, we have now completed the entire series chapter for Cambridge AS Mathematics 9709/12. From we did arithmetic progressions and all the way till geometric progressions to sum to infinity to Cambridge applications, and that's one of the biggest pure math chapters finished. Our next topic is also one of the most important in the entire syllabus, which is going to be part of calculus, that is going to be differentiation. And after that we will only be left with integration, and hopefully, as per the target that we give ourselves, we should be done by the entire syllabus coverage by the 24th of July, hopefully, and then we'll move on to covering S1. So many students think, so in differentiation we are going to cover, where in differentiation, the math changes from sequences to rates of change, the gradients, optimizations, and the applications in the real world, tangents, stationary points, and modeling, where your quadratics is also going to connect with how we find the turning points and whatnot. Many students think calculus is difficult. It isn't. If you understand the ideas from the beginning, it becomes one of the most logical chapters in the whole course. If there's a quadratic, so you are going to find what at this particular point x naught and y naught, what is going to be the gradient of the tangent, which we call dy by dx. The admath students are going to find it extremely easy. The ones who come from O level math background, their CAIE background, they are not, they can also catch up in just it's only a matter of one lecture. The ones who did their GCSE math, they also know some application of calculus, very brief. So we will go in depth, and they will realize that why they derivate in the manner that they were taught right now. So if you understand the ideas from the beginning, it becomes one of the most logical chapters. So make sure you're subscribed, turn on notifications, and don't miss the next lecture, which is going to be on Thursday on differentiation. And like I always say, you go to your Cambridge endorsed book. If you don't have the digital copy, you can reach out to me on my WhatsApp and I will send it over to you. My WhatsApp number is +92 329 3028485. It is also mentioned in the Instagram, in the bio of our Instagram, and our Instagram handle is EASY Taleem, TALWM. Everything is for free. So if this lecture helped you, or before that, if there is anything that you find confusing, you can put it in the comment section, and I will make sure that I respond to that. But if this lecture really helped you, you share it with a friend who's preparing for 970912 for either October November 26 or May June 27. I'll see you in the differentiation chapter on YouTube. Take care.